Alright, this is Mr. Yeager, and this is the final lecture on optics. And what we're looking at today is basically how your eyes work, the idea of why people are nearsighted and farsighted, how can we correct that, and a very brief definition on polarization. So, with this, the eyes. Okay, it's very brief. If you're in anatomy, you're probably going to learn a lot more than this. All right, from a very basic standpoint, with the eyes, the lights will travel through the cornea, through the lens in your eye, and focuses on the retina at the back of your eye. All right, so if I make basically a very rough drawing of an eye, okay, we have your eye, and then inside your eye, basically we have these muscles that are holding a lens in your eye, a convex lens. And then you have your retina in the very back. So very rough drawing of the eye, sorry. So you have the cornea, you have your lens. I believe these are called like the ciliary muscles. And then you have the retina in the back, and then the retina is connected to the optic nerves. All right? And so the idea is the light should come in, get refracted, then basically get refracted even more fine focus refraction, so that in the end, the light will converge on the retina, produce an image that your optic nerve then will obviously send to the brain for your brain to then interpret. All right, that is basically what we are looking at here. All right, so the cornea itself, going back to that drawing, it has the largest change in the indice of refraction that occurs. That goes back to what we talked about before. Okay. The light's coming from air. That's going to be n equals 1. As it enters your cornea, it's going to be a very large change. I mean, it could be something as large as like n equals 3, n equals 4. That's considered a large change. Okay, it's probably not that high in my opinion, but what we're saying is there's a large difference in the index of refraction. All right, and we're going from low density to high density, low density to high density. And what that's going to do is it's going to cause the greatest amount of bending of that light. And we need that so that it can go through your lens. That will not be as large a change in the index of refraction. Okay, going back to this page. But it will cause what's called the fine focusing. All right? It's just like if you've ever worked with a camera. All right? You know, I used to have to teach camera and eye mechanics, basically how similar they are. With a camera, there's a rough focusing and a fine focusing lens. All right, the rough one obviously changes very much. It changes it quickly. Fine focusing does very small changes and obviously will make the image as clear as possible. All right, so the cornea is your rough focus, lens is your fine focusing. Now the thing is, this is where the camera obviously differed. Your camera is specifically designed with one type of lens. Obviously there are ways to change it up, obviously, but like it can't change when you're trying to take a picture and go, oh my gosh, you need another lens. You're going to have to take some time. Your eyes can adjust. And your eyes adjust because they have that muscle connected to the lens. And it turns out when the muscle contracts, all right, basically when it pulls, all right, when it contracts, it will cause the focal length to get shortened. All right, it will shorten that focal length so you can try to see particular objects. When the muscles relax, the focal length will lengthen, and that will help you see objects farther away. So when the muscles contract, focal length shortens. That means obviously everything has to be focused at a close proximity. When it's longer, you can try to hopefully see objects clearly. Again, we're talking about clearly. You might see color, you might see some blurs, but do you see it clearly? That all depends on how well that image, that light, focuses all on the retina. All right? What happens if it doesn't focus correctly on the retina? What if those light rays are not completely converging, and because again, in order to see an image, you have to have two light rays completely intersect. What if they are just barely apart? Well, then you start seeing some blurriness, and you might be nearsighted, which is called myopia. This is when your focal length is too short to focus the light on the retina. All right? This usually has to do because of the shape of the eyes. All right? So it's not like, you know, I mean, it is genetic. It's essentially based on the shape of the eyes itself, where just unfortunately even the muscle can't stretch it enough or can't compress it enough. It can't change it to the appropriate length to fit on the retina. Now again, this is only in particular situations. Nearsightedness, all right, basically say you can only, you can only see things that are close to you. You have trouble seeing things farther from you. I always feel like I messed that up, so I apologize if I messed that up. All right. Yeah, so it's too short to focus light. So on farther objects, it's going to be too difficult to make it basically land on the retina. And so what happens essentially is you have your cornea, you have your lens, and you have your retina. What happens is the focal point is basically before the retina, so when the light comes in and bends, all the light rays converge before the retina. So when it hits the light hits the retina, it's already spread back out, and things seem pretty blurry. So that means farther away, objects are definitely a little bit tougher to see. Okay? It's a little bit tougher to see. So this is corrected with a concave lens. This is corrected with a concave lens. Because a concave lens will basically create a virtual image that seems like it's closer than it is. Okay? If you think back to when we did the ray diagram, and you have your object, the virtual image shows up right here. Basically what they're doing is an object that is a little bit farther away, basically your eyes are able with the lens to focus on something, because again, the lens is in front of your eye, all right, basically creates an image of that object closer to you, which your eye can then appropriately see, and basically push this focal point onto the retina itself so that you can see very, very clearly, all right? So a concave lens will help push that, again, it doesn't change, it doesn't, we're talking about small changes, but it'll help that faraway object, basically it kind of tricks your brain to think that you're focusing on it closer than it is, and therefore then you see it very, very clearly. All right? Farsightedness, hyperopia. This is where the focal length is too long. Images form past your retina. So what happens here is the focal point is beyond the retina. So basically as it hits the retina, the light has still not completely converged. It hasn't come together. And so therefore, this is obviously makes it more difficult for somebody to see something up close. The image, something close to them, is being seen past their retina, and the retina is interpreting light that hasn't converged yet, that hasn't combined. And therefore, it's not as clear. Okay? So, this is corrected by a convex lens, in front of the eye. Convex lens in front of the eye. And what happens here is, if you recall, you have that object, that image is actually projected farther away from the object. So it actually backs it up, and again, that's what you can see clearly. It basically then tricks your brain with it. Now, people have asked about like other types of eye defects in terms of, the people that say they're farsighted in one eye, nearsighted in the other. Obviously, optometrists, ophthalmologists, they'll help design these glasses to obviously adjust according to what your eyes specifically need. Even within the lens itself, there can be areas of the lens that are thicker, therefore convex, and areas where it's thinner as the light travels through, so it can appropriately focus with your eye. All right, so that's the eye. Very last topic, very brief. We have what's called polarization of light. You probably have heard of polarizing sunglasses, okay? And the idea that these will help you see images or see things clearer. It'll help reduce glare. That's actually one of the key things. All right? Polarization itself is the production of light in a single plane. All right? So I have my drawing underneath here. Light actually is always being produced this way all around us. It's in all different directions. It's not just straight up and down. Some is side to side, up and down, at angles, left and right, all over the place, all right? For the most part, we can obviously interpret all this. Our eyes themselves help essentially focus all this. But the thing is, this can create glare if you're trying to look at something from farther away on glass or something else, because basically the light's not traveling through well, okay? Your eyes can't maybe completely focus on it. And so what happens is polarization is occurring right here. This is a good image of it. Essentially what you do is you create basically a barrier that will only allow one type of plane light come through. And so all the light that is basically, as you can see, the thicker red one right here, all right, that one is in line with this particular grate, this particular polarizing substance, okay? And so what happens is that will produce only one plane of light, which is a lot easier to focus, and therefore you can then see it very, very clearly. You don't get that glare produced as much, all right? And I mean, other examples is basically like, you know, if you have a slit that's only like this, okay? You're only going to be able to get light through that's up and down, up and down, up and down. That will travel through. Anything going side to side, it's going to get blocked by the barrier. So that only one plane of light is able to make it through. That's what polarization is. Really the main thing there is it's a single plane of light and it will help reduce glare. Those are usually the two main questions. All right, so very brief. That's it. That's the end of optics. Thank you.